Welcome to the Space Academy. This module marks the beginning of your flight into the awesome world of space exploration while enhancing your English. We aim to equip you with some foundational knowledge related to space, science, technology, engineering, mathematics, and communication. You'll explore the universe and develop essential language skills tailored to your aspirations in future technologies. So sit back, strap in, and enjoy the ride. Mission objectives. Have you ever wondered how astronauts and ground control teams communicate during a space mission? Effective communication is crucial for ensuring the safety and success of missions. In this lesson, we will explore the essential communication skills and vocabulary used in space exploration, focusing on how astronauts relay information to ground control and receive instructions in return.
Imagine a spacecraft approaching the International Space Station for docking. The astronauts aboard the spacecraft must follow precise instructions from Mission Control on Earth, which monitors their approach using telemetry data and provides real-time guidance. However, midway through the docking process, the communication link between the spacecraft and Mission Control suddenly fails. Without communication, the astronauts wouldn't know if their approach speed was too fast or if their trajectory had shifted. Even a small misalignment could result in a collision that damages both the spacecraft and the ISS.
Unable to receive corrections from ground control, the astronauts might hesitate to make adjustments, unsure if their own instruments are functioning properly. They could attempt to continue docking blindly, but any miscalculation could lead to disaster. Google Maps as we know it cannot work in space. It relies on GPS signals, which are satellite-based and designed to function within Earth's atmosphere and immediate orbital environment. While satellites like GPS are used to map and provide data about locations on Earth, there is no infrastructure to extend this to outer space navigation in real time, at least not in the same way. However, NASA and other space agencies have their own mapping and navigation tools, such as star trackers and specialized space navigation systems, which help spacecraft navigate vast distances by locking onto stars, planets, and other celestial objects. For example, NASA uses tools like the Deep Space Network to communicate with distant spacecraft and track their positions. These systems work beyond Earth's orbit, but are much more complex than Google Maps.
The term anomalous can refer to something that is considered unexpected or doesn't follow model procedures, especially during missions. Lack of effective communication could endanger the mission and the lives of the crew. Astronauts are dependent on real-time data and instructions from Mission Control to ensure safe and successful space operations. Without effective communication, you may have a serious problem.
Later, we'll discuss some missions where there were serious problems. The story of Apollo 13 became a textbook case for how vital communication is in space exploration and the extreme measures needed when there is a problem. The term textbook often refers to something that is considered a perfect example or follows a model procedure, especially during missions. For instance, when a maneuver or mission goes exactly as planned, it may be described as textbook, meaning it unfolded just as it would be described in instructional materials or training scenarios.
Telemetry is the process of collecting data from remote or inaccessible locations and transmitting it to receiving equipment for monitoring and analysis. In the context of space missions, telemetry involves sending vital information about a spacecraft's systems, instruments, and environment back to mission control on Earth. This data helps ground control make informed decisions about the mission's progress and the safety of the astronauts. Next, we'll explain how it works.
Telemetry systems use sensors to gather data from various instruments on the spacecraft. These sensors can monitor temperature, ensuring systems are functioning within safe limits; pressure, monitoring the atmosphere within the spacecraft and its various systems; electrical status, checking the status of power systems and batteries; location, using GPS or other positioning systems to track the spacecraft's trajectory. Once the data is collected, it is converted into a format suitable for transmission. The telemetry system uses radio waves to send this data back to Earth. Ground stations receive the signals and decode the information, allowing mission control teams to monitor the spacecraft's health in real time. Ground stations are placed all over the world so they can talk to satellites as they move in the sky. This helps make sure the signals are strong and travel quickly.
My name is Florence Tan. I'm the SAM Electrical Lead Engineer. I work at Goddard Space Flight Center. SAM stands for Sample Analysis at Mars. It is an organic chemistry lab on the Curiosity rover. It is the most well-equipped chemistry lab that we've sent to Mars to date. Curiosity landed on Mars on August the 5th, 2012. It was born on Mars that day, and so we consider that day as its birthday. We're here at the testbed lab where SAM is built. It is an identical unit to the unit on Mars, and we use this unit to test our experiments before it is transmitted to Mars. SAM will be running some great science experiments on Mars. We will be analyzing some soil samples. To make the soil samples go down, we had to program it to vibrate at various frequencies. When we're introducing a sample into SAM, it'll go through a resonance and it'll sound like this. To commemorate SAM's birthday and Curiosity's birthday on Mars, we decided to play a little song. If there's anyone listening on Mars, on this special occasion, you will hear this. It's really neat and it's exciting. This is a first for NASA and for the world. And music brings us all together, so this is fun. It's been a great year on Mars, and I cannot wait to get to Mars Sharp next year. We've discovered so many new things, and there's still lots more discoveries to come.
During the Apollo missions, telemetry data was crucial for monitoring the spacecraft's systems, providing mission control with information on everything from fuel levels to the astronauts' vital signs. This allowed ground control to offer real-time support and make decisions based on the spacecraft's condition. Rovers like Spirit, Opportunity, and Curiosity rely heavily on telemetry to communicate their status and the results of their scientific observations. Engineers analyze this data to ensure the rovers function correctly and to plan their next moves on the Martian surface.
Houston, we've had a problem. We've had a main B bus undervolt.
Roger, main B undervolt. For econ? Negative, flight. I believe the crew reported it. We got a main B undervolt. Okay, flight, we've got some instrumentation flights. Let me add them up. Roger. Okay, stand by, 13. We're looking at it.
And we had a pretty large bang associated with the caution and warning there. And as I recall, main B was the one that had a amp spike on it once before.
Roger, Fred.
So you want the wide beam width there?
Yes.
Let's see if we can correlate those times. Skip the time when you want the wide beam there, Info.
And the interim here, we're starting to go ahead and button up the tunnel again.
Roger.
During the Apollo 13 mission, after the explosion damaged their spacecraft, the spacecraft was off course. Normally, they would use their computers and instruments to steer, but many of them were broken. As they didn't have their regular navigational instruments, they used the Earth itself as a visual guide. They aligned the spacecraft by looking out of the tiny window at the Earth's position, a true old-school approach in the vacuum of space. The crew used basic principles of astronomy and their instincts to guide the spacecraft back to Earth.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
4%. Challenger, go at throttle up. Challenger, go at throttle up. 1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles. Flight controllers here looking very carefully at the situation. Obviously a major malfunction. We have no downlink. We have a report from the flight dynamics officer that the vehicle has exploded. Flight director confirms that. We are looking at checking with the recovery forces to see what can be done at this point.
I feel like I'm losing my mind. Is everybody in the world blind? Please, Lord, give me a sign, a sign. Is everybody in the world blind? Please, Lord, give me a sign, a sign.
I wanna be the greatest. Everybody on the